So while we're sorting out the slides, she's going to go without slides.
All right, well, hello everybody. So I'm going to start this out as a bit of a lecture because we've got some technical difficulties. Some quick bits about me. I'm a very recent graduate at UC Santa Cruz, where I conducted my undergraduate research with Peter Alvaro. I did some work with Disorderly Labs while I was there. Prior to that, I had interned at Twitter, designing and implementing automated fault discovery and recovery for their core storage systems. And previously interned at Google Research with the machine perception branch. And these days, I'm in AMTS with the emerging database group at Salesforce. And today I'm talking about absolutely none of that. I'm actually going to be talking about some of the work I did for my undergraduate thesis in the last year. I think it's a fair conjecture to start that all of you in this room probably want some degree of consistency for your systems. While it might vary the degree to which you want it, the implementations by which you achieve it are going to vary. And invariably, it's going to be really difficult to do. We all try our best to optimize for our workload to make good on the promises that we make. But it's really difficult to know once we've done it right, if we've done it right, to figure out whether we're there or not. And we do this in a few different ways. We do some really careful engineering. We apply tests, be that unit tests or functional tests or stress tests. We recruit experts to really prod and poke and try to break our systems, and we try to exploit the pitfalls that are inherent to them. But at the end of the day, it's still really difficult to know whether or not we've got it right. And there are a few different ways people examine the quality of their systems, one of them being serializability checking. And before I get into much more, I just wanted to give some quick, really high-level, informal definitions for people in the room, because we're going to be talking about histories and how to procedurally generate them. And it would be really good to start with a quick overview of what a history is. At a high informal level, history is a collection of transactions which are themselves a series of reads and writes over a set of named registers. Beyond that, we're going to be talking about how to generate non-serializable histories. And we'll classify serializability as, a history is serializable if, when you reorder its transactions and you execute those results, you see equivalent effects to running those transactions in a sequential order. And a quick last sub-definition here. This work today focuses specifically on view serializability. There are a few different degrees. But in this case, we're going to be talking about view serializability, which concerns itself with visible effects as opposed to the order of those conflicting operations. So bearing all that in mind, there are a few different reasons why we might be interested in checking serializability. A lot of distributed SQL-like databases guarantee strong consistency and snapshot isolation. And Kyle Kingsbury, who has given a talk on just this, his work alone suggests that few manage to actually make good on those promises when you expose them to stress. What we really need are tools to really help confirm our databases work like they're promised. And like any test, Jepsen can empirically confirm rather when they don't. Jepsen and tools like it are increasingly a common way to do things like this. And I see people start to weave them in with their development processes, which is wonderful. They offer a lot of insight into the underlying systems with this black box approach, really prodding the system from the outside and seeing what we can intuit about its innards. And at a high level, that's basically how it gives us that insight. It does its worst to try to thwart our systems. Jepsen is going to throw some really bad, some pessimal executions at our system, the worst even. And there is a second component, Gretchen, to Jepsen, which will then analyze the histories that are output by Jepsen. It'll basically see, after all of those terrible things that we did, do we still have serializable output? Were we still able to make things okay in the end? And that's actually worked out pretty well for people. Working from a black box system, we can actually glean a lot of information. We know that these consistency guarantees are a hell of a lot harder to uphold than we anticipated. And as much as it might hurt our egos and hurt our systems, recognizing these pitfalls has actually been pretty good for us. It lets us slowly arc towards the robust and correct systems that we really want. And this effect this approach has been super effective. And naturally, we see wider adoption. But as such, it would be really nice to understand the guarantees that we really receive when we use this as a way to test our systems. And so Gretchen, this serializability checking component, faces a lot of difficulties, and many serializability checkers face similar ones. While Gretchen doesn't have to verify strict serializability, there are still many different ways through which we can violate weaker serializability models. And it would be nice to have some assurances as to which of these violations we're actually able to detect with a tool like that. We want some way to test our tool to evaluate exactly what we learn about our system when we're using it. It's kind of like we're using this meter stick to measure the efficacy of our system, but we're not really certain about the dimensions of that meter stick itself. And before we draw any assumptions by its output, it would be nice to really see what we're getting. So we've got to do this meta-testing in the dark. We have to figure out some way to know that these tests are correct. Is it possible that some test could have made a mistake, could overlook a bad execution, could say something was fine when it wasn't? And we really need to find some way to ensure the accuracy and coverage of their conclusions before we really use them to guide our development of systems. So we'll move to drawing up some tests, and this requires us to really evaluate what makes for a good test. And I would contend that regardless of what system you are testing, you roughly look for the same kinds of components. It all really boils down to a handful of qualities, the first of these being coverage. You want to have some notion for the cases that your tool can address correctly. We want to show the boundaries of our tool. Beyond that, we want to look at coverage. We want complexity. Simple tests are very nice, they make us feel very good, but they don't really reflect the complexity of the content that our tool is going to face. We want our tests to be really meaningful. They should be sufficiently complex that they can model the content that we expect to encounter when we're running it. And beyond that, we want tests to be general, and this specifically for...
Can we copy the presentation?
Yeah, absolutely.
Yes.
And we would like our tests to be general beyond that. So especially for something like Jepsen, which is going to be dealing with a lot of different systems. Give me just a moment, I'm downloading this. So we're going to be testing a variety of different systems, and we can't necessarily make any sorts of assumptions about, what the internals of that system are like. We're not guaranteed to have unique rights. We're not guaranteed to have unique transaction IDs, and it makes tracing those systems and it makes wrangling those histories much more difficult. And so we have a few different options, bearing that in mind, what we'd like for a test. So, first option being, you could irradiate data, for instance. You could randomly create different kinds of schedules, different histories. And while this might give you quite a few different unique anomalies, you have no guarantee of what those base cases are. On top of that, while they might be very complex and very general, you're really lacking, oh no, I didn't know. What we really lack is coverage. Alternately, we could actually work from real non-serializable histories, which in fact match our systems, match the complexity that we would anticipate them to deal with. And beyond that, we know are sufficiently complex. We know contain at least some anomalies. But in addition to giving us incomplete coverage, we have this issue of overfitting, where yes, we're optimized for the output of this particular system, but you want Jepsen to be versatile, and constricting it to that kind of testing is not the most useful thing you could do. Yes. The third option is you could really lovingly craft some terrible histories. You could make them thousands of transactions long. You could really embed these anomalies, and you can make them very complex. And that's wonderful, but a really cruel thing to ask of your developers, and intractable given how many things can go wrong and how difficult that is to get right. And while all of this sounds very sad, there is a fourth option. The talk does go on, and it's a generative approach to crafting these non-serializable histories. Now, when I say generative, I'm talking about from a classification of the fault space of distributed executions. So a lot of my work I had rooted in this thesis by Atul Adya, which was put out in 1999, which is weak consistency, generalized theory, and optimistic implementations for distributed transactions. What this means for us is basically presented different classes of anomaly and faults that you can witness at different levels of isolation, and classified them as their sets of minimum witnesses. We're going to refer, they're basically very compact specimens of these serializability violations. You're going to be on slide 18. Oh, okay. And we can't just take them as they are. So we're going to treat them like, There we go. Okay. So we're going to treat these as seeds. We'll refer to them as kernels throughout this talk. And we can't just take them as they are. What we're going to need is to grow them into something much bigger and much hairier and much uglier, and that can be tough. But it's worth mentioning some of the things that we won't touch. Since we're testing from an outside standpoint, we have to work with this, the limits on black box implementations. You're working with these observed effects. You can't necessarily see into the heart of the machine. And so we won't have support for indeterminate transactions, which may succeed or fail. I'm not sure why this is jumping around. Which may have succeeded or failed, nor will we have it for phantoms. But what we will be looking at are violations of view serializability. Just to say, write-write conflicts, where two conflicts will overwrite some key with some value. Read-write or write-read conflicts, where you have some cyclic dependency. Oh, this doubles up on the jump, very weird. In which each transaction reads some value that another one has written, and you have these anti-dependency cycles, in which one transaction reads, which is then overwritten by a following transaction. So it might be easier to visualize some of these, just to say, Ti and Tj may update the same variable, and we model this we're going to refer to this as a directed serializability graph. This is the minimum witness that is put forward in some of Adya's papers. This is the DSG, the minimum witness for a cyclic dependency. I'm not certain why these are jumping around. Bear with me. And finally, we've got these anti-dependency read-write conflicts. And this is going to be a conflict of anti-dependency in which a transaction reads some value. Oh, my goodness. OK. So putting option 4 in practice, we're going to select one of these kernels, one of these base cycles of two transactions. And we're going to treat that as the seed from which our very ugly history will grow, the seed of our test case. And what's nice about this is it gives us a strong root in coverage. We understand exactly which cases we're building from as we expand outward. We're going to see that expansion is actually very difficult. We can model a lot of these problems with just two transactions, which is nice, but is ultimately not realistic. It's not what we see in practice. It's not what we end up seeing in practice. And when we perform an expansion to try to make our histories look like what is output by a distributed testing tool like Jepsen, the output of your systems, we can cause a lot of complications. So there are a couple of different ways to perform expansion. When we've got the cycle that we're starting from, we can either increase the cycle itself, increase the size of that loop, or we can increase the breadth of the graph. We can add spurs, which don't have downstream effects on the cyclic conflict. There are going to be restrictions to the addition in this. Sorry, I'm trying to figure out this clicker. It's a very weird technical thing. OK, so this can cause quite a few complications. Namely, we can morph one conflict into another if we add the wrong kind of dependency when we're expanding these cycles. So for instance, the difference between a write-write cycle and a cyclic dependency is the difference of a single edge, a write-read edge. And when we're trying to increase the complexity of our cycles, we risk losing the coverage. We risk the guarantee that we cover the case that we began with, that we are trying to expand. And so there's this base compatibility between them. Spur additions being the most permissive, however problematic, as we'll see later on, for these anti-dependency cycles. They lend quite a bit of width to the graph and can help obscure the cycle itself. Cyclic attenuation can morph the kernel type into a different one altogether. And so we have these different compatibilities. There's kind of this succession between them where anti-dependencies are the most robust and can tolerate additions of all different sorts, can wind up with very interesting graphs. And circular dependencies require some care as well. So as we move forward, basically, when we're performing expansion, we need to be mindful of both the location and the context of these transition interactions, or these transaction interactions. OK, so this is an expansion of a cyclic dependency. So between A and B, there is a write-read dependency. I'm actually going to just put this down, because I don't know why it's jumping. So we've done this. Is it?
It's playing it, yeah. It's like it's playing every slide, so it switches every 5 seconds. Right.
Oh. Can I? OK, that's so much better. Thank you. All right, we don't have to race between slides anymore. Okay, so this directed serializability graph is an attenuated version of the cyclic dependency graph. What we've done is gone ahead and added some cyclic additions. So we added onto the cycle corpus, more or less adding links onto this chain. And we've only selected, as you can see, for ones that connect A and B in this cycle, compatible edges, right read or right types. Meanwhile, for the spur additions, they're not connected, they are connected to the cycle, but they have no way to loop back and around or rejoin the cycle, so that they won't actually morph the content of that cycle. What we've done so far is basically given ourselves the option of, all right, so we've got the base case that we would like to cover. And in our expansion, we've strived to maintain its, its integrity, making sure that we add only compatible edges and spurs. We're building out a wider tail for us to explore. But this might seem like a much simpler problem than it actually is. It's really tempting to say, isn't this the solved issue of cycle detection? It's a really wonderful and lovely thing that we can posit with some of Aj's work. And as much as I wish that were the case, the answer is no, it isn't. We really can't make assumptions, like I said before, when it comes to unique transaction IDs or unique rights, which is an assumption in Aj's work. Sometimes from this outsider standpoint, we really can't differentiate between the source of a right. So for instance, if two transactions both write x equals 1 and some transaction later reads x equals 1, there's ambiguity as to whose effects we're witnessing. And this problem can't be really condensed into cycle detection when you've got this potential dependency, these potential lines where it's not really clear where the lines of that graph really lie. And what this gives us is a difficulty when it comes to generality, and it's actually kind of how we deal with that, how we wrangle with systems that may provide less information about the origin of their transactions. While it's really viable in theory to do cycle detection, what we end up having to do is implementing what we will call maybe edges or hyper edges, which denote potential dependencies between these transactions. And what this will look like in our graphs is this. We expand our directed serializability graph into what is called a hyper-directed serializability graph. It involves the addition of these edges, and we denote them in dashed lines. Basically, these rights that are implemented here are installing the same value and introducing some ambiguity as to where that value may come from for transactions that observe those effects later on. So, putting that together, through this approach, what we attempt to do is assure our coverage by selecting the kernel case that we would like to model, and then very carefully attenuating that cycle, adding to its breadth and its depth, using compatible edges, using spurs, and obscuring the conflict itself while retaining its quality, and then fuzzing data in the right ways, in the right places, so that we still retain that coverage. Coverage is the hardest thing to lose, or the easiest thing to lose as you're expanding the cycle. And adding these maybe edges and mutating them. And so we've got this bigger history with a lot of ambiguity to it. And what this looks like in practice, what this looks like in implementation, translating into theory, is we start out with this directed serializability graph of two transactions. You pick your initial kernel cycle. And this will be the one from which we grow. We're going to start modeling that and move into expanding its complexity. You're going to start manipulating that graph based on type. We're going to modify it with some degree of randomness, spurs, or increase the dependency edges within the cycle. We begin by constructing, with some probability, an edge and a transaction. And depending on its location, we'll select a relationship type that is copacetic in the cycle. And for spur additions, we actually run into this issue where, while they may be very viable in every other cycle case, during anti-dependency cycles, you can actually create a serializable history from non-serializable beginnings by offering a path right around the cycle. You can find your way out of it. And so you can have your spurs go for a long time, lead on a lot of red herrings, have a lot of breadth in that graph, but eventually cull them back in at some point into that cycle. So what this looks like for the initial expansion is moving from this into that directed serializability graph, adding the complexity in different modes of depth or width, and this can be kind of a configurable thing. You can model different sorts of workflows. From there, we have to then select different edges for fuzzing. And this requires a little bit of care. So before we can really turn that directed serializability graph into a trace that could have been produced by some black box system, We need to lose or forget information that's going to be categorically unavailable to a testing tool like that. The key uncertainty here, again, stems from the fact that we really only know a read-read conflict edge exists if we see some transaction wrote a value and something else witnesses it afterwards. The intuition is that if we have the second value, if the second transaction read a value written by the first, it has to follow in history. And so when we're selecting an edge, we pick some write-read edge, and we pick some second transaction which is reachable from that edge, not necessarily its next neighbor, but something who could feasibly witness its effects. We'll then delete an edge that we selected and replace it with some hyper-edge. We'll choose some number of other hyper-edges to write that same value and give them the common destination transaction as the original edge, and we'll give that a write-read classification. And that's very abstract, but in practice looks, sorry, jumping the wrong slide, looks like this. From there, we've actually got this complete hyper-directed serializability graph, which is great, but does not resemble the Lisp that we're going to have to turn this into. This is the actual output of some of the histories that come through Jepsen, modeled as a set of transactions and operations with their reads and writes. And so what we then need to do is bring concrete values for those keys, for those values down, and have them reflect the relationships that we've created in this graph. What we'll first do is iterate through the different conflict edges, the concrete conflict edges that we have of the DSG, iterating through all of them that are not hyper-edges. From these, we want to select variables and values to comprise the operations that are represented in each conflict type. For read-write conflicts, so for write conflicts, that's going to be a common variable selected. 2 unique values will be assigned to that same key. For write reads, this is just going to be source transaction will write some unique value which is later read by a following transaction, by some subsequent one which accesses the same variable. And then for read-write conflicts, the source value is going to select some key that's previously been written to, or either read its initial state and is going to alter that, install some x prime. And then, only then do we get around to iterating through the hyper-edges. Once we have concrete values assigned elsewhere, we can start having those maybe edges install those same values. We'll select all of those with the common destination transaction and have each write some common value to their one common key, which is then going to be read by the destination transaction. Basically, this yields some trace which denotes a history that is very in line with the Jepsen history, which we saw before, which is going to say it's comprised of transactions which are possessive operations whose function, either read or write, affects some key, installs some value, and we've determined all those values to just reflect those relationships that we classified through that process of graph generation. And while this has been lovely, there's still a lot more I would have liked to do had I the time. It would have been nice to add more structural options for how we expand those directed serializability graphs. Beyond spurs and just cycle elongation, it would be really nice to be able to make some suppositions about, okay, well, if we have a more robust system that does offer us some metadata about transactions, that does offer unique writes, that does offer transaction IDs, why not give them the option to try out more robust testing? We could provide support for phantoms. We could provide support for aborted transactions, have a larger variety for expanding our DSGs. We could alter different branching decisions and try to model different workflows and be able to see if we can optimize, different tests for different, or how our testing tool is able to handle different kinds of workflows, what confounds it, what is comfortable for it. And moving beyond just view serializability, giving complete coverage to the other classes, the other specimens that are offered in Adya's work would be a really exciting thing. So, if you've managed to stick with this, despite all the technical difficulties, despite the initial lecture, despite the slide jumping, I hope, if nothing else, you're able to take this away. Fact of the matter is, the way that we are testing to ensure that our databases work, the way we think they do, is really evolving, and that's really exciting. It's wonderful, but it should be taken with caution as well. We really want to know what guarantees we receive from it. And that involves us taking a closer look at these systems too, these testing systems. And that by starting from anomalous kernels, we can distill what's a really intractably large space that we're asking them to explore, that we're asking them to prod our systems with. we can turn it into a handful of test cases and really look at what wide coverage is like, what our systems are capable of doing, set our expectations in a more concrete way. And by growing those kernels into histories that mirror the reality that our systems have to reckon with, we can increase the confidence that we have in those test cases, and as a result, increase the value of those testing tools for us, expand their capability and their accuracy, expose weaknesses, and account for them. Okay. Are there any questions? I have no idea what time it is in terms of this talk since we've been jumping around. Okay, thank you.